All right, so before we start, I wanted to make sure that you're aware of the Student Advisory Panel. This is a semesterly event that we hold along with the Student Advisory Board. This Friday from 11 to 1, free pizza, of course, but it's a forum where you can come and ask questions or express concerns or make suggestions on programmatic changes. So not, I mean, you can talk about your individual classes or whatever, but it's really more for programmatic changes. And if you don't feel like you want to, come to a public forum and speak about it, you can always, of course, contact your student advisory board representatives, and they can bring up the issues on your behalf and keep you anonymous. You would be able to contact them by actually joining the Discord, the CSAB Discord. So I would encourage you to do that if you haven't already. I'll be there, of course, because there is free pizza. Right. So, last time we were looking at this challenge. This challenge is to print out a countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. But the two items that you're not allowed to use are loops. You can't use any for loops, while loops, do while loops, no loops at all. And no hard coding, right? So we can't just, cheat and print out 10 things, or 11, I guess, for the blast off, right? So what do we have available to us? Well, we've got, conditions. We can still use print statements, of course, because we got to print it. The only thing left in my mind is a function, right? Well, we before we even do that, we can determine if n is equal to 0, right? This is just a regular old conditional. If it's 0, then we can of course print off blast off, right? And we're good. Right? Otherwise, we'll want to print the number, right? And so I can say printf %d end the line, right? And n. There we go. So at least I've got that part, right? If it's a number, we print it in a countdown. If it's 0, then we'll go ahead and print blast off there. Now, if I were to compile this, of course, it's not going to give me what I want, right? It's just going to print out 10, right? It's not making any progress towards that blast off condition, okay? So I'm not allowed to use loops. I'm not allowed to do any hard coding here at all. But what do I have left? I have functions, right? Well, okay, I could put this chunk of code here into a function called, say, countdown, right? That takes an integer n here because I'm not going to declare it, right? And I've got something that looks like this, okay? So if I were to call countdown here, I would have the same result. All I've done is moved this code off to a different location, right? When I get into this, of course, it's 10, so it gets printed, the number, and then it returns. I'm not making any progress. There's no way for me to print 9, 8, 7, 6, 5, 4, 3, 2, 1. But I do have a function here that will print some sort of a countdown. Right? How could I use that? Right? If I down here, if I said countdown n minus 1, countdown n minus 2, I could achieve the challenge, but again, I'm hard coding these values, right? So, where else could I call the function? Inside the function itself.
So check if n is 0.
Right. Yep. Set if n is 0, then we blast off, right? Otherwise, if it's not, say it's 10 or 9, 8, 7, whatever, right? I'll print it out because I do want the print statement there, but then I'll make a decision to count down the next value, n minus 1. Right? So this is a function that calls itself. It's self-referential. And we call that recursion. Right? So that's what this module is about. So today and probably Friday here. Right? Let's see what it looks like. GCC and run it. So actually before that, let's predict I don't want these now, sorry. Let's predict what it's going to look like. N is 10, and I call this function countdown. Right? And it receives the value 10. It's not 0, so it's not going to print out blast off. Instead, it's going to print out 10, and then it's going to call countdown on 10 minus 1. In other words, 9. Right? That, in turn, is going to call countdown on 8, 7, 6, 5, 4, 3, 2, 1. Right? So it achieves what we did, but using no loops at all. Right? So let's go ahead and take a look at this in Python Tutor and see how it is actually achieving this. Get rid of all that and just go with this. So let's walk through the code once it's done. There we go. All right. So we're about to call countdown. N is 10. We call countdown. What happens when a function calls a function? A brand new stack frame is created on the top. So it'll end up printing out 10, right? And then we end up calling countdown on 10 minus 1. So we call countdown again. How many n's do you see, by the way, at this point? 3, right? Each one of these is a completely different variable because it's a completely different stack frame. Stack frame on top of stack frame on top of stack frame. Now, it is growing down, but that's just because that's how what the HTML looks like, right? It's not really up, down, left, or right, because it's just a computer. It's just a concept. Right? 9 will end up calling countdown on 8. 7, 6, 5, 4, 3, 2, 1. Let's go halfway. There we go. We're at 3, right? And it's too much to visualize at that point. There we go. Now we're on 1. Now we're about to we're about to call 0. There we go. Come on. No. Did it already print? Nope. Okay. We're about to print blast off here because we're going to be calling countdown on n is equal to 0. There it is. N is now equal to 0. And then it's 0, so it ends up printing blast off. Right? Now, what's going to happen when I return from this function? In fact, what's going to happen when I return from each one of these? I've built up these 11, 12 stack frames. What's going to happen when you start returning? They get popped off, popped off, popped off. Right? And I'll just fast forward here. You see that it goes the opposite direction. So in other words, instead of writing a for loop to do this, or a while loop, right? What I've done is I've abused the stack space to keep track of each different value. Right? Each different stack frame has a copy of, or its own variable called n, each with a different value. Right? So we achieved our goal, but who cares, right? Anybody here could write this for loop pretty easily and put it into a function. So in case you think that this is a toy example, the example itself is a toy example, but there are languages out there where you don't have for loops. You don't have while loops. In fact, you may not even have variables. Instead, you have functions and only functions. They're called functional programming languages. Lisp, Scheme, Haskell. And they either don't have these kind of control structures, or they highly discourage them, or discourage their use. We're not going to go that far because this is not a functional programming language, obviously. It's what's called a procedural style programming language, C is. Why? Because you have statement 1, statement 2, statement 3. It's how we think about processes, right? If you were to make a peanut butter and jelly sandwich, right, then you have this process that you follow, step 1, step 2, step 3. Right? You don't eat it before you put the peanut butter on it, right? Functional programming languages force you to think more like a mathematician. And even though my undergraduate was in math, I still don't think like a mathematician enough to program like a mathematician. And that's why these languages aren't really all that used ubiquitously. Right? They're certainly not going to be in the top 10. But recursion is still a thing. Like I said, it comes from functional programming languages. Functional programming languages are influenced by math. So let's take a look at what recursion looks like in math. Google image search here. Let's go with fractals. There you go. And let's just look up at images. Right? So there we go. There are these nice little images that are all. These are called self-similar mathematical objects. That's looks like an interpretation of the Mandelbrot set. But the one that I want you to focus on right here is this. This is called the Sierpinski triangle right here. In fact, let's look up a better version of it. Sierpinski triangle. Right? And this is the one I want. Right? Let's take a look at that. Oh, come on. I can't zoom in anymore. Fine. I'll just go ahead and move over here. Zoom in. Okay, I can't scroll then if I do that. But there, I can scroll over. All right, the idea here is that you start with an equilateral triangle, and then you follow the following rule. You draw an equilateral triangle in the center, and you take it out. You repeat that rule on the remaining 3 triangles. You repeat that rule again on those remaining triangles, those remaining triangles, those remaining triangles, etc. In other words, it's a self-reference thing. I will take myself and I will modify it. Then I will modify pieces of myself until when? Well, as far as fractals are concerned, forever, right? Can we have a program that will do this forever, that always call itself? Keep going, right? Yeah, what's going to happen then? So let me go ahead and put this outside the loop, right? Will this work? Actually, let's do it like this. I wonder what would happen now. Right. So I call it on 10, we call it on 9, we call it on 8, we call it on ... Do I ever get... I get down to 0 at some point, right? Countdown of 0. 0 minus 1 ends up calling countdown on -1. Do I ever actually get to the point where I check what value n is? Nope. So let's go ahead and n minus 1. Let's go ahead and see what happens here. Oops, sorry, GCC. There we go. A.out. All right. So what happened there? A segmentation fault. That tells me that it was a memory thing. Right? What I want to do is I want to show you what's actually happening here. Right? So let's go ahead and start with a different value here, -1. Right? So let's predict what's going to happen. I'm going to come into this and it's -1. Is it 0? Nope. So I will end up printing -1 and calling it on -2, -3, -4, -5, right? Eventually when it wraps around, sure, because of overflow, but let's watch it. Now it's actually doing something. We're going to get the same segmentation fault eventually here, but after 261,000 calls. Remember the visualization. What are we doing? We are creating stack frame upon stack frame upon stack frame until we made 261,000 stack frames. At that point, our stack is full. What happens? Stack overflow. Right? So this is runaway recursion here, right? And you can have runaway for loops, right? You can have runaway while loops. Those are just infinite loops. In this case, though, I'm not only have an infinite recursion, but I'm abusing the call stack to do it, and eventually it comes back to bite me in the form of a stack overflow and segmentation fault. These things go on forever, infinite, right? And they define fractal dimension or fractional dimension, right? Another example, you've probably seen it before, let me go ahead and just get rid of that, is the Fibonacci sequence, right? It's always the go-to. So what is the Fibonacci sequence? It's from math. Right? It's a sequence that is defined in terms of itself. So the value f of n is equal to f of n minus 1 and f of n minus 2. With these, what are called base conditions here. The first Fibonacci number is 0, the second one is 1. Now, how do you compute the second Fibonacci number? You just take the 2 previous and you add them together and you get 1. How do you compute the third one? You take the 2 previous, 1 and 1, and you add them and you get 2. 3, 5, 8, on and on and on. But does it ever end? Well, this Wikipedia entry ended. But does the actual sequence ever end? No, it's an infinite sequence. So we have to be really careful here because from the realm of math, recursion refers to infinite things. Infinitely defined things or never-ending sequences, infinite sequences. What we need to do as far as code goes is we need to make sure that there's a stopping condition. Otherwise, we'll have an infinite loop, right? So what is recursion? Why do we call it recursion, right? In general, recursion is something that references itself. And the classic joke here is I don't use Google, I use DuckDuckGo, but well, they don't have this joke. So let's go ahead and go with recursion because Google, at least back in its heyday, before it turned evil, was written by geeks like us, right? Their mantra used to be do no evil or do no harm or something like that. And they've now thrown that out the window big time. So what is recursion? Tell me, Google. Oh, did you mean recursion? Yes, I meant recursion. Did you mean recursion? Yes, I meant recursion, right? It's self-referential. right? And so it's a joke that they built into their search engine, right? So that's what recursion is. And again, it comes from math originally, but in coding, it refers to a piece of code that either refers to itself, or in the current context that we're looking at it, it is a function that calls itself one or more times, right? Again, mathematics fractals are similar objects. And we also have, what I just showed you was the Fibonacci sequence. I'm going to write it out here using some mathy stuff. There we go. F of n is equal, it looks like I've done 0 here, or 1 for 1, and n is 2. So I've skipped the first one. It depends. Oh, do you start it at 0 or do you start it at 1? Right? 0, 1 or 1, 1. All I'm doing here is cutting out the middleman and starting it at n is 1. Okay? It's going to be the same exact sequence. Otherwise, the nth Fibonacci number is equal to the n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. Right? And again, the sequence is going to look something like this, at least the way that I've defined it is 1, 1, 2, 3, 5, 8, dot, dot, dot. And that dot, dot, dot means that it goes off into infinity. Right? So let's design our own recursive function to compute the Fibonacci number. Right? This is always the go-to. Anytime that you see recursion in a computing class, it's usually, hey, here's the Fibonacci sequence. Okay, why are you looking at the Fibonacci sequence? Because it's famous and it's related to the golden ratio, and there's this famous guy, Bonozio Fibonacci, that came up with it, whatever, right? Okay, well, what use does it have? None, right? But a bad example, it can still serve as a good example for why you do not do recursion. And that's going to be my demonstration here today, right? So every recursive function, first of all, needs a base case, right? That is a case where you no longer do any recursion, because if you just kept doing recursion, what happens? You are in an infinite recursion, and you will eventually overflow your stack space, right? So base cases may need to be used for error handling as well, right? If I go back to this this countdown here, right? One base case that I could have had here to prevent you calling this function on negative values would be n is less than 0. And instead of printing, or instead of continuing, I'll say printf error, right, or whatever, right? That's not error handling, at least it's not proper error handling, but you get the idea, right? Now my program is robust. It doesn't matter what you give me. Either it'll print error, blast off when I get down to 0, or it'll print the countdown, right? GCC, right? And run it, and now it's error, right? I could, of course, start this at 20 instead, right? There. Now we've got a 20, 19, 18, dot, 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 blast off. Right? I could start this at 0. What's going to happen now? You just immediately blast off. All right? So you need base conditions. Some of those base conditions may be for error handling. Right? And you need to make one or more recursive calls, and each one of those recursive calls must make progress towards the base conditions. All of this should sound absolutely familiar. When we introduced loops, I said that loops have 3 components, 3 main components, and then, of course, the body of the loop. An initialization condition. How do you get things started? I called countdown with 10, right? That's my initialization condition. I got it kicked off by calling this function. All right. 2, a termination condition, where you no longer iterate through the loop, or in this case, where you no longer make any recursive calls. 3, making progress towards that termination condition. Where is that here? Right there, -1. I am working towards 0, assuming that I've got a positive number. Right. So recursion is nothing more than loops being hidden by you abusing the call stack. Right? All right. So let's go ahead and go through this this exercise here. This is always the exercise, right? Let's go ahead and create a function for the Fibonacci sequence. Fibonacci, there we go. And instead of, well, here, what should my n be? I don't know, 5. So what would that be? That's 1, 2, 3, 4, 5. Let's do something else. 6, I'm going to be expecting I'm going to be expecting Fibonacci Fibonacci of 6 should be 8, right? According to this sequence right here. 1, 2, 3, 4, 5, 6, there's 8. Okay? That's what I'm going to be expecting out of this thing. So let's call that function Fibonacci on n, right? And let's capture its value, int result. And let's print it out. Result is equal to %d and the line, and result. Right? Now, you help me design this function. I call it Fibonacci because that's what it is. Right? Not very useful at all. Right? It's useful as like a coding exercise, yeah. Right? But it's going to be even more useful to us when I illustrate why you don't do this. All right. So what should the return type be here first? Yeah, because what are those numbers? Are they floats? No. It's an integer. All right. And it takes as input a single integer n. Okay. All right. So what's the first thing I should do? Following the same pattern as before. You need one or more base conditions, base cases, where you don't do the recursion anymore. As far as the Fibonacci sequence is concerned, what are those base cases? 1 and 2. So, if n is equal to 1 or n is equal to 2, what should I return? 1, 1. Right? So I should return 1. There we go. Else, all right, what do I return? The n minus 1th Fibonacci number and the n minus 2th Fibonacci number. Well, we have a function that will compute the nth Fibonacci number, so we can call that Fibonacci of n minus 1, right? And we can add that to Fibonacci of n minus 2. Right? And then, of course, we could store that into a variable. I'll do that. I'll store it into a variable here, and then I'll simply just return x. Right? If you want to write shorter code here, you can just go ahead and return this expression. Right? But I'm going to store that in a variable here because we're going to have a use for it later. Okay? Are there any other base conditions I should consider? So is it defined for negative numbers? No. So you could put in a negative, a negative value in there, right? If n is less than or equal to 0 or less than 0, whatever you want. It depends on how you want to start the sequence. Then we could return, I don't know, some flag value here indicating that something went wrong. -1. Okay. Let's go ahead and compile this and see if it works. Now remember, I'm calling it on n is equal to 6. The 6th Fibonacci number, at least according to my definition, should be 8. Ah, wonderful. All right. Let's actually move this into a command line argument so I can play around with it. Argv, excuse me, of 1. Right. And let's go ahead and get rid of this. Let's make sure that it still works with 8. Oh, oops, sorry, 6 is what I had. All right. 6 gives me 8. Let's continue. 7. What should it be then? What's next? 13. Ah, it works. If I go up to 8, that should be 8 plus 13. We've already tested it, 21. What if I go up to 9? What should it be? 34. Okay. 10, 55, 11. Okay. 12, 13, 14, 15. Are these correct? You do the math as we go along here. You tell me. Yeah? Okay, 16. All you have to do is add the last two numbers here. All right, 17. So that's 1,597. Looks like it's working to me. All right. Let's just go ahead and go up to 40. All right. Does that look right? I don't know. What could we look at? Wolfram Alpha? All right. So what is the 40th Fibonacci number? Right. And we're going to be off by 1, so 102334. Oh, hey, all right, cool. It did work. But how long did it take? It wasn't that bad. It was noticeable. It was barely noticeable. Let me go up to 45. That's only 5 more, right? How long should I wait for this? Okay. Wow, that was actually quite quick. Not what I was expecting there at all. But 1, 1, 3, 4, 9. 1, 1, 3, 4, 9. Okay, good. Let's go up to 50. So did you notice the time delay from 40 up to 45? Right, it got a lot slower. Right. I can almost guarantee you that this will take hours, if not days or weeks, to compute if I let this go. And not only that, but we'd eventually get overflow. Right? So why is that? Well, think about what's going on here. Let me open up an image. Where's Fibonacci tree? There we go. All right, so suppose that we call Fibonacci just of 5. Right? Fibonacci of 5 is going to make 2 recursive calls. One of them to Fibonacci of 4 and the other one to Fibonacci of 3. Each one of those makes 2 recursive calls. Fibonacci of 3 and Fibonacci of 2, Fibonacci of 2 and Fibonacci of 1. Each one of those makes 2 recursive calls. 2 recursive calls, 2 recursive calls. This is only 5. Now imagine 50. What would that tree look like? It would be of depth 50, but how many, and we call these leaves down here at the end, how many leaves would there be? Something on the order of 2 to the 50. All right. Well, from alpha, you tell us. What is 2 to the 50? All right. All right. Big. 10 to the 15th, something like that. Actually, I can tell you exactly. It would be the 50th Fibonacci number. It would be exactly that value. So it'd be 10 to the 10. We call them billions. All right? Is it done yet? Oh, it did. It did billions, right? How many billions? 1 billion, right? Or 12 billion. It did 12 billion operations. Obviously, it did not give us the correct answer. Why? Well, because we hit overflow. It's a very large number, right? It's 12 billion. If I went up to 100, right? There we go. It's exceedingly fast today. I did not expect that, right? But I can guarantee you that this one will not execute. There we go. So that goes up to 10 to the 20th operations, which we call quintillions. Right? No, it's not going to work. Let's look back to our tree here. How many times do you end up doing the same operation over and over and over again? For example, how many times do you actually call Fibonacci of 2? I see 1, 2, 3. Right? How many times do you end up calling Fibonacci of 1? 1, 2, 3, 4, 5. Right? Do you see a pattern there? 3, 5. The number of times you end up calling things follows the Fibonacci sequence itself, which gets huge, right? By the time I get to the 100th Fibonacci number, right there, 10 to the 20th, something like that. Right? Now let's take let's consider that number, and suppose that we were doing maybe 12 billion. Let's go 12 times 10 to the 9th. That's 12 billion, right? Right. Operations per second. Well, it took us more than a second, right? But let's suppose that we've got an even faster computer that can do that. Times 60 seconds, times 60 minutes in an hour, times 24 hours in a day. So here is a very low estimate on how long that would take. Right. So that's days. Let's go with 365.25 days in a year because of leap year. Next year is a leap year, so plan accordingly. There's just a hand wavy estimate of how long that would actually take. 935 years. Right. Okay, good. I'm not a liar. Right. It's still going. Right. It will go for another 1,000 years if we let it. Right. Because it won't hit a stack overflow because we're only going to a depth of 100. You can make 100 recursive calls. Right. In fact, we saw that you can make up to 260,000 recursive calls. So we could find the 260,000th Fibonacci number. Right. Can you, Wolfram Alpha? Yes, you can. Right? 10 to the 54,000, right? These are orders of magnitude. We're never going to get this. So let me kill it already. Right? And it's because we have this naive recursion that computes the same thing over and over and over again. Right? So that's one of the main drawbacks of recursion. Before we get to the drawbacks, of which there are many, is there any good? In fact, the good, right? So recursion can be useful or good, right? Many divide and conquer style algorithms are presented as recursive. Divide and conquer, right? I don't know how to solve this problem, so I'll go ahead and take this problem and divide it into two problems. Now I've got a smaller problem. I'll take that problem and divide it into two problems. Now I've got an even smaller problem. I'll take that and divide it into two problems. Now I've only got one problem, right? And I can directly solve that. Once I've solved each one of those, maybe I can make an entire solution out of it, right? So it's good to think inductively. You're probably not taking 235 right now, but you might have seen mathematical induction, right? It's a way of thinking about problem solving and by divide and conquer, right? Many, like I mentioned before, many programming languages encourage or primarily use recursion because they don't have loops. Right? This is how you have to do it. They force you to think like a mathematician, right? Whether you want to or not. The other argument is that recursion can lead to clean or simple or beautiful code. Right? I mean, look at the Fibonacci sequence as an example. Right? This is a nice mathematical definition here. It has virtually a one-to-one translation over here into my code. Right? That's nice. That's clean. That's beautiful code right there. Right? But what about the bad? Recursion. The bad. Right? You risk overflowing your stack with runaway recursion. Right? You even if it isn't runaway, right? In other words, infinite, then you are still abusing the call stack. If I had written a regular old for loop for that countdown exercise, there would be one variable, right? I. For int I equals 10, I is greater than or equal to 0, I minus minus. But because I used the call stack, how many variable copies were there? As many as, as n, 11, whatever it was. Right? So you're already abusing the call stack, which is limited. In fact, organizations like, say, NASA forbid the use of recursion in their systems. Why? Because of risks like this. Right? And finally, you can have a naive exponential approach to the problem, where you are recomputing the same things over and over and over again. Right? So how do we get past all of these problems? And by the way, you can see a pattern here. The good, those are all really subjective arguments. One person's beautiful code, one person's clean code is completely different as another person's dirty code or ugly code. Right? That's a value judgment right there. Right? A human value judgment. A divide and conquer style algorithm, you can actually take any recursive, eliminating recursion. You don't have to have recursion. Any recursive code-wise function can be rewritten as a non-recursive function. Right? Just using a for loop or a while loop, or simulating the recursion, or simulating the call stack. Right? So you don't actually need it. In fact, some programming languages don't allow you to, or older programming languages. The first versions of Fortran, I believe, did not support recursion. Right? You can always use regular old loops and data structures, to simulate recursion. Right? So you don't actually need that. There's another technique called called tail recursion. Right? And the tail recursion involves eliminating variables or writing the recursive variables so that a compiler can compile away the recursion automatically for you. Basically, instead of having 10 stack frames to do a countdown, it uses one stack frame and then reuses that stack frame over and over again. Right? We won't get into that. Instead, we'll get into another technique called memoization. Memoization, right? It is spelled like that. It is pronounced like that. It is not memorization. And the basic idea here is that you can use recursion, but you store, in other words, you cache results so that they are not recomputed. In other words, that naive way of doing it, where we just go ahead and make multiple calls to Fibonacci of 5, billions of calls to Fibonacci of 4, right? Instead of doing that over and over again, what we're going to do is we're going to take those results and put them into a table, a cache, right? You store results into a table, right? In other words, a cache, right? When you need to compute a value, let me go to the next line here. When you need to compute a value, you do the following: check the table or cache, right? However you want to call, whatever you want to call it. If already computed, use it. In other words, no recursion. Do not make a recursive call. Otherwise, if not, then yeah, okay. Pay for the recursion, right? But after you've paid for it, after computing it, store it in your table so that the next time you need to compute it, you look it up, right? This is called a lookup table. It's called a cache, right? We're just going to call it a table, right? Or in our case for Fibonacci, we're going to call it an array, okay? So as our example, eliminate or use memoization to compute the Fibonacci numbers. All right. So I'm not going to let's focus on this function first of all, right? So I want to compute Fibonacci of n, but I also want a table of values, an integer array of already pre-computed values, right? We won't worry about the size of that. Right? We'll just go ahead and keep this edge case here, right? If you gave us something bad, then we'll go ahead and give you something bad, -1, -1, right? Otherwise, if it's these are base cases, I don't do any recursion here at all, so we can go ahead and keep those as well. Otherwise, I'm going to check, right? Check to see if values of I or n has already been computed. ... So I need an if condition. If it has been computed, use it. In other words, return it. Return values of n. Okay? Otherwise, else, values of n, which is equal to Fibonacci of n, has not yet been computed. ... So what we'll do is compute it. Right? That's why I was using x before. I need to store it. So Fibonacci of n, and passing in my values, my table values there, and table values. Right? And then once I have it, I don't immediately return it. What I need to do is I need to store it. Store it. Cache it. Right? And what I'm going to do that is values of n is equal to x. Right? So next time you need Fibonacci of n, you're not going to compute it. Instead, you're going to find it in that table right there at the nth index. Okay? And then, of course, I return it. Still recursive, right? But now we're using this table here, and we're memorizing the values. This is why it's called memoization. It is a form of memorization. I don't know what the root of that word is. It's probably just made up, right? How do I check to see if it's already there? So if values of n has been defined, ... Right? So I could use how did I do it up here for invalid values? You gave me something invalid. I'm going to give you something back to indicate that, no, that's not possible. It's not defined. Right? -1. Right? -1 will be our placeholder. Right? -1 will be a flag value indicating not yet defined. Why? Because do you see a -1 in that sequence there at all? Nope. There is a 0 if you go with the Wikipedia definition of Fibonacci here, so we can't use that. But we will use -1, right? -10, -42, whatever. Right? Just some flag value that indicate that it has not yet been defined. Right? So how do I translate that to this? If value sub n is not equal to -1, then it's already been computed. Go ahead and use it. Okay. There is my working towards the termination condition, right? There is my termination condition, these two right here. Right? Now, where is my initialization? I need a table of values. Okay. How big of a table do you want? Well, first of all, how do I create a table? Table here being an array. Okay, I'll call it values here. Malloc, int star malloc, right? And because it's integers, size of int. Oops. And how many of them do you want? N. Careful here. Remember 0 indexing. Right? If I want to define 1, 1, 2, 3, dot, 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 up to n, 1, 1, 2, 3, 5, 8. Let's just consider those right there. What Fibonacci of value would that be for? 1, 1, 2, or sorry, 2, 3, 4, 5, and 6. So if you wanted to compute the 6th Fibonacci number, right, how big of a table do you actually need? Remembering that in code, we've got another guy over here, 0, which is undefined, at least as far as we're concerned. So how big do you actually need it? +1. It's not because of the null terminating character. These are not strings. Don't get that confused. Right? It's just the same trick here. We need one more. Right? We all good? All right, well, let's find out. Oops. Yeah. It doesn't realize that we are actually returning. Oh, wait. No, do I have something wrong? Say what? 40. Oh, sorry. 46. What? Values. I've got misplaced parentheses here somewhere. Oh, there we are. There. Always look to what you just wrote. I did not end that else statement. There we go. All right. A dot out. I don't know what's the 6th Fibonacci number here. 0. Ah. Okay. Why? We can actually compute the 100th number. We're not going to get a meaningful value here, but it is going to work, and it gives us 0. So it gave us the wrong answer, but at least it gave it to us quickly. Right. What's going on here? What values are stored in that value table as of that line right there? Line 44? Dead beef? Who knows? If you get lucky, zeros. Does 0 indicate that it has not yet been computed? Nope. So now that we're using memoization, we have to set up everything to say, I've not computed the first Fibonacci number, or the second, or the third, or the fourth, or the fifth. So for int I equals 0, I is less than or equal to n. Actually, let's do it this way, n plus 1. I plus plus. A little bit more idiomatic for loop there. Value sub I is equal to -1. We have not yet computed it. Right. GCC. Let's try something that will work here. 8. What's the next one? 13. 21. 34. Which one did work? 40. Right. Remember, it was just slightly noticeable. Now it's immediate. 45 was even more noticeable, maybe a few seconds, but now it's immediate. 46 is going to be even slower if we went with the traditional way of doing it, but now it's immediate. 7, immediate. Well, now that we've gone overflow. For your exercise next week when you do recursion, we are not going to be using integers. Instead, we will be using what are called longs, right? Or maybe longs, right? I think long is enough. The difference between an integer, which is 32 bits, means that you have a maximum value of, do you remember what it is? 2 to the 31st, because we need one of those bits for a plus or a minus, positive or negative. And then minus 1 because we start at 0. That's the maximum value that you can represent, 2.147 billion. With a long, you have 64 bits, right? So you have 2 to the 63rd minus 1, which is much, much larger. What do we call those? Quintillions. Let's come back over here and change all of these ints to longs. Long, all that's good. And instead of integers, they're going to be longs, long, and long. Did I do it up here too? Nope, there. Long. I think that's good. I think this is going to be LD. GCC. Nope. What should it be? I need a long here. Sorry. There we go. There. So the placeholder for a long is a long digit. LD. All right. So let's try 47 now. Oops. Nope. What's wrong? GCC 47. Should be able to handle that. What's going on? The X values? Oh. Well, what do you mean X values? Oh, thank you. Yep, we were being truncated, and that's what killed us. There we go. All right, Wolfram Alpha, are we right? What is the 47th Fibonacci number? 2971. 2971, and that's good enough for me. Right? Remember 50? Did 50 work? I forget. It did? All right, there we go. Let's go up to, I don't know, 60. All right. That's immediate. What's the 60th Fibonacci number? 1548. 1548. But in contrast to the previous program, this would probably have taken hours, days, weeks, some estimate there, right? We're not going to get the correct answer here, but the thing that would have taken, what was it, 935 years? We'll get the correct answer. Well, we'll get the answer back, but just not the correct one. But we'll get it really, really quick. What we need is a larger number. So there is a long. In some systems, that's going to be a 128-bit number. Beyond that, though, you need to bring in a library to do it. They're called multi-precision libraries. And these multi-precision libraries can support arbitrarily large numbers, right? And what happens is it just uses software to store all this stuff instead of using the hardware. So there's a huge performance hit, but at least you can go ahead and represent the 1000th Fibonacci number, right? Which is something like that. Right, there we go. Lots of digits there. 208 digits to be precise. Right? So you can do stuff like that. We'll pick it up there on Friday.